All right, this mini lecture is going to look at a physics law known as Hooke's law. And it is essentially the behavior of springs and how the force caused by a spring, what that's related to. All right, so any elastic type material like a spring, we're going to use springs as our example. All right, so I want you to imagine that you have a spring. And if you had a spring sitting there and it's attached to the wall, so you're holding it on one hand, there's sort of a state that it just is happy, that it's its natural length. So every every spring has a natural length. And when it at its natural length, it doesn't do a whole lot. You can touch it, it doesn't do a whole lot. But when I change the length of the spring, we start to experience an interaction. So if I'm going to interact with the spring, I'm going to apply a force. It's interacting with me, it's applying a force, and that interaction works through that change in length. So, how do I change a spring's length? I have two choices. I can either, I'm going to put the natural length up on that spring. I can either squish it, which we call a compression, or I can stretch it, which we call stretching. So compression is shortening the length of the spring, and stretching is strengthening it. All right, well, first let's look at what the force that it takes for me to do that, to either compress it or stretch. How that's related to the force that the spring is exerting. Well, if I'm interacting with the spring, if I'm compressing it, then it's interacting with me. So it too is exerting a force. How do those forces compare? Newton's third law tells us that they're equal and opposite. So the first thing to think about is that the force by a spring is opposite how we're changing that spring's length. If I am compressing the spring, in this example to the left, the spring is pushing to the right. If I am pulling the spring, the string is pulling me back to the left. So the force by the spring is opposite the change in length. So if I compress it, it's going to be pushing to the right. If I stretch it, it's going to be pushing to the left. All right, so that's the first thing. It gives us a little bit of indication about the direction of that spring's force. Well, what is the magnitude of the force related to? Well, imagine taking a spring and you pull it a little bit. And then you pull it a little bit more. And then you pull it a little bit more. And then you pull it a little bit more. Does it get harder or does it get easier? The more you pull it. It gets harder. The further and further and further I try to change my direction, the more difficult it becomes. As I increase my change in length, I increase the force required. Is that true for compressing it? If I have a spring and I'm squishing it, and then I want to squish it a little bit more, then I want to squish it a little bit more, yeah, the more I change its length from that natural state, more force required. And if it's more force required by me to do it, then the spring is exerting more force back on me. So if I increase the change in length, I'm going to increase the force. All right, well, what else might change the spring? We've all had different kinds of rubber bands, right? Some are real flimsy and easy to stretch, and some are much more difficult to stretch. And then there's those ones that come like on the stalks of asparagus, And they're really hard to stretch, right? So what is it about those rubber bands? They kind of all look the same. Well, they're made of different materials. Every spring has a property of the material itself that defines how stretchy it is. We call that the spring constant. The spring constant is a property of the material that gives it its stretchiness. So, the property of the material for the stretchiness. That is, we use the letter K as our spring constant variable. All right, so if I increase K, I increase the amount of force. If I increase the stiffness, it's harder to stretch the spring or compress it. So these are the two things that are related to the force by a spring. And if I put these two relationships together, well, the force is directly proportional to both of them. So if I increase K, I increase the force. If I increase the change in length, I increase the force. So it's directly proportional to the both of them. But we want to remember that it's opposite the change in length. So we're given our direction. This is what's known as Hooke's law. It defines the force by a spring. So let's look at that as a specific example and then just see that that negative makes some sense to us. I'm just going to erase this bottom part. We're going to look at these two situations. We're going to define our natural length as x equal to 0. If I compress a spring, and we'll use just this orientation. So I'm going to have my base at the left, and I'm going to compress the spring in that direction. This is my final location of the spring end. The force by the spring is equal to minus K delta X. We expect this force to be in what direction? To the right. So let's see if this relationship works. Well, my X final is to the left of 0. So negative K, let's just work this out, X final minus X initial is delta X. Negative K, X final is to the left of the origin. So that's a negative value. X initial is 0. So negative minus 0 gives me a negative delta X. Two negatives give me the force of the spring is positive. And it's equal to the value K delta X. So Hooke's law gives us not only the direction, this value is positive, also the magnitude, as forces need to have both. Well, does the same work with stretching? In this case, there's my X final. Oops, I'll stretch that spring a little bit more. So the force of the spring is equal to minus K delta X. Minus K X final minus X initial. Our delta X never changes, right? It's X final minus X initial. In this case, X final is positive. Positive minus 0 gives me a positive delta X. This tells me that the force is negative, and indeed, in this example, it's pulling to the left with magnitude equal to K delta X. So Hooke's law gives us that direction. But Hooke's law is pretty intuitive as well. Okay, so remembering that the force is related to the spring constant and remembering that the force is related to the change in the length of the spring, whether you stretch it or compress it. The direction of the spring force is pretty intuitive. If I'm pushing against the spring, it's going to push in the opposite direction. If I'm pulling on the spring, it's going to pull in the opposite direction. Then you have to use your coordinate planes to determine the true direction in terms of positive or negative, depending on, of course, your initial conditions, as all of our problem solving has depended on. All right, so that's Hooke's law. Good job.